Welcome to the next session, my dear friends. So in the previous session we have discussed about the decreasing growth method, and now we are going to learn the logistic method and simple graphical method, comparative graphical method. So what are the rest of the methods of population forecasting that we are going to learn now? Okay. So logistic curve method is a bit empirical method, so you need to remember the formulas, but as far as gate is concerned, it is not that much important method. So it is not needed to remember and memorize all those formulas. So the method is there, that is why I am explaining. See here, logistic curve method. So I told you already, there will be a saturation population and there will be a population at any point of time. Okay, so there will be three populations here in logistic curve method. So this is PS. So at any point of time, the population you are having, that is PT, and the initial population is P0. The initial population is P0. These are the three populations we are having in logistic curve method or any method we want to discuss. So here the equation, the relationship between these three populations is given like this: ln PS minus PT by PT minus ln PS minus P0 by P0 is equal to K into PS into T minus K into PS into T. So this was a relation derived from that graph. This is the relationship which was derived from the graph. So by solving this relationship, we will get the value of PT as, PS by 1 plus m into u to the power of nt. So P by 1 plus m into e to the power of nt. This is the formula we will get. So for example, if you know a population of three subsequent time intervals, so for example, let T0 at a T0 that is equal to 0, initial at T0 is equal to 0, let the population is P0. Okay, P is equal to P0 and T is equal to T1. Okay, T is equal to T1, the population is P1. Now T is equal to 2T1, then the population is, let T is equal to T0 is equal to 0, that means initial. So let the population is P2. Then the saturation population. So this, from this equation here, this is PS. So from this equation, if you derive population at any time, so we need to know PS, we need to know M, we need to know N. So the formula of PS, M and N can be derived from this population data. So PS is, saturation population is defined as 2 P0 P1 P2 minus P0 square into 2 P0 P1 P2 minus P1 square into P0 P1 square into P0 plus P2 divided by P naught P2 minus P1 square. P naught P2 so from this formula, so we will get saturation population 2 P naught P1 P2 minus P1 square into P naught plus P2 by P naught P2 minus P1 square. So from this formula we will get the saturation population. So this is what saturation population. Now the M value, so we got PS, now we need M and N. So M is equal to PS minus P naught by P naught. M is equal to PS minus P naught by P naught, and N is equal to 1 by T1 ln PS into P naught minus P1, PS into P naught minus P naught into PS minus P1, P naught into PS minus P1 by P1 into PS minus P naught, P1 into so this is the value of N. This is the value of 1, N, 1 by T1 ln P naught into PS minus P1 by P1 into PS minus P naught. So this is N value. So if you know PS, M and N, you can determine the population at any point of time T. So this is an empirical formula to determine the population. So this method is called logistic curve method or logistic forecasting technique. So but this method is not that much important for GATE examination, as this method is present. So we need to discuss this concept also. Otherwise it is not necessary for GATE examination. Okay. So let us go to the next method, that is simple graphical method. Simple graphical method. Again, these graphical methods are also not important for exam, because graphical kind of questions they cannot ask in the exam. So that is why these things are also conceptually important, problematically they are not important. So simple graphical method is nothing but if you plot a logistic curve. Okay, so for example we will be having a logistic curve of any location up to the latest census, that is 2011. So we are having latest census up to 2011, we will be having data. So if you want to forecast the population of 2021, then you need to extrapolate it. So using the extrapolation technique, so usage of extrapolation technique is nothing but simple graphical method. Simple graphical method is simply extrapolating technique. Simple graphical method. See, so you are having a logistic curve of population and time. Let the graph is like this. Okay, let the graph is like this. Now, so this is up to some year of 2010. Like, let us take it as 2010. You want the population of 2050. You want the population of 2050. Just extrapolate with the same slope. Extrapolate with the same pattern. Just extrapolate. Extend this graph. Then this will be your population in 2050. So this is simple graphical method. Whatever the graph we are having up to present data, so we will extend that graph and just draw a projections onto the x and y axis. You will get the population. So this is one method. This is simple graphical method. Okay, this is a simple graphical method. It is simply extrapolation based on the previous data. Okay, extrapolating future population from previous data. Okay, using the logistic curve. Using logistic curve. So this is nothing but simple graphical method. So what is the comparative graphical method? Comparative. What is comparative graphical method? See, for example, there will be growth rates for different cities. So for example, this is the growth curve of city A. This is the growth curve of city B. I want the growth curve of city C. Okay. So now city A and city B are very old cities. So for example, here the population of city C, so if I take a straight line like this. Now, so for city A, for city B, for city A, so the same population. So all of them are having same population. So let P1 is a population, P2 is a population, so P3 is a population. So same population I am taking. So this P1 population is achieved by city A in the year of 1950. Okay. So the population P1 is achieved by city A in year of 1950. And city B, it is somewhere around 1960. Okay, it is around 1960. So here city B, city C, it is achieved this in 2000. It is achieved this in 2000. Okay. Similarly, some different population P2, it has achieved in 1960. It has achieved in 1970, so it is achieved in 2010. Now for this city, what would be the population of 2050? 2010, I want the population of this city in 2050. So definitely the population of 2050, that is 40 years from here, that means look at the population of cities A in the year of 2000, look at the population of city A in the year of 2000 and look at the population of city B in the year of 2010. So it will be in between the populations of city A and city B in the year of 2010 respectively. So likewise, this is comparison. See how this growth. For example, if this is Mumbai, this is Delhi, and this is Pune. Okay, so now, so the city growth is comparison, it is in between Mumbai and Delhi. So like this, so what is the population of Pune in the year of 2050? So likewise, we can find using the comparative graphical method. So establishing a comparison between two different cities which are having a same growth pattern in the early stages. So that is what the comparison. So this is why this is called comparative graphical method. This is comparative graphical method. Okay. So these are the different techniques we are having. These are the different techniques we are having to forecast the population. So now what is over so far? So from where we came into this population? To find the sufficiency of the source. To find the sufficiency of the source, we need how many are the users. So in order to determine the number of users in the future time, that means till the end of the design life. So we need these techniques to identify the number of users at the end of the design life of the component. So that is why we are using forecasting techniques. So now the forecasting is over. So now we have a knowledge of forecasting the population. So how many population will be present at the end of the design life of the component, we can now find. Now what we need is, so how much water is needed per person. Now the next topic which we are going to learn is rate of demand. So the next topic is rate of demand, or simply the water demand or per capita water demand, whatever it may be. So the next concept is rate of demand. See, water demand or simply rate of demand. Now, how to calculate the rate of demand? How to calculate the rate of demand? So we cannot go to person and ask how much water you need, how much water you need. So can we do it like this? No. So it is a very lengthy process to go and find everyone household how much water is using, or go to industry and ask how much water they are using. Instead, we will be having a data how much water we are supplying. So we know the present population and what is the water they are taking from us. So we are supplying the water, so we will be having a data of amount of water supplied, as well as we will be having a data of how many users are using this water. So these two data will be with you. So we can calculate the per capita water demand. We can calculate the per capita water demand. The per capita water demand is equal to, so total amount of water total volume or amount of water supplied to a community for an year, because the more data you take, the more accuracy you will get, because there will be daily variations, there will be seasonal variations. Okay, so that is why, so we will consider the data of total volume supplied per year divided by, so number of heads using this water, that means persons, that is population, and number of days you are calculating, 365 days. So the total volume or amount of water supplied to a community for an year in liter. Okay, so this is called head. Population means what? Head, or we call it as capita. So capita or head, both are same. This is day. Is day. So the unit of per capita water demand, the unit of per capita water demand is liter per head per day. Liter per head per day, that is LPHD. This is LPHD, that means liter per head per day. Similarly, we can write this as liter per capita per day. This is called LPCD, liter per capita per day, that is LPCD. That is LPCD. So, using this formula, we can find the per capita demand of water of a community. Okay, this will be total demand, including domestic, industrial, public use, all the demands. So, if you want to find separately, so we made analysis that how much is needed for domestic use, how much is needed for public use, how much is needed for institutional and industrial use. All those things we have calculated and framed the values in a form of a code which we refer during the design of any kind of structure. Okay. So as per the code, Indian Standard Code 1172/1993, as per IS 1172/1993, so they have classified some important varieties. There are many demands they have given, so I am only telling you the broad classification of demands. Okay, so one is domestic demand. Domestic demand. So this demand value of water varies from 135 LPCD to 200 LPCD. 200 LPCD. So this is for low income group and this is for high income group. So this is also LPCD and this is also LPCD only. Okay, so this is domestic. Domestic means bathing, cooking, washing of clothes, cleaning of floors, whatever it may be. Now all these things 135 and 200 LPCD for LIG and HIG. Industrial or institutional water demand. Industrial, institutional water demand. So it is taken as 50 LPCD for industrial and 20 LPCD for institutional. So jointly it is 70. 50 plus 20. 50 plus 20. So that is 70 in both the cases. In HIG case as well as LIG case. So because it is irrespective of LIG, HIG, industry and institution is not relevant to the both income groups. Now next is public use like lawn sprinkling, okay, gardening of public parks and all, that is public use. Public use, we keep 10 LPCD for both the income groups, for high income group as well as low income group, because it is irrespective of those things. And losses, so there will be losses and thefts. So we keep 55 LPCD because of various pipe bends and elevation differences, drops, whatever it may be the reason, leakages. So for incorporating all those things, we keep this losses and thefts as 55 LPCD. So if you add up this, you will get 55, 60, 190, 270 LPCD. This will be 270 LPCD and this will be 335 LPCD. So this is the per capita water demand exclusive of fire demand. There is another demand, see here, this is only conventional demands, regularly happening demands. The domestic and industrial, institutional, all these demands are conventional. It happens regularly on daily basis. But fire, it won't happen every day, everywhere. So it happens all of a sudden at different localities. So that is why we don't consider the fire demand as a regularly happening demand. We keep it aside and we will calculate the fire demand in another way. We will discuss it now. So these are the rate of demands. Rate of demands. So let us also discuss the fire demand now. So how to calculate the fire demand? So fire also needs water. So how to calculate the fire demand? See, fire demand, there are many empirical formulas. And all the formulas are important for the exam. Empirical formulas, but it is important for the exam. You need to remember the formula. There is no other chance. You need to by heart them many times. And also during the memorizing the empirical formula, you need to remember it with the units. If you forget units, then there is no need of remembering a empirical formula, because empirical formula is unit sensitive, so you need to remember the units. So empirical formulas to determine fire demand. Determine fire demand. The first formula is Kuchling's formula. The first one is Kuchling's formula. Q is equal to 3182 square root of P. Q is equal to 3182 square root of P. It is Kuchling's formula. And the second formula is Freeman's formula. Freeman's formula. Q is equal to 1136 into 1136 P by 5 plus 10. This is Freeman's formula. Next is National Board of Fire Underwriters formula. National Board of Fire Underwriters formula. Q is equal to 4637 root P 4637 square root of P to 1 minus 0.01 P 0.01 root P. This is National Board of Fire Underwriters formula. And fourth one is Boston's formula. Boston's formula. Q is equal to 5663 square root of P. P is equal to 5663 square root of P. In all the formulas, you need to substitute the P in thousands. P is population in thousands. P is population in thousands, and Q you will get it in liter per minute, liter per minute, or LPM. So you will get Q, the requirement of the water in terms of liter per minute, and the population you need to substitute in thousands. For example, if the population is given as 1 lakh, okay, so for 1 lakh population, for 1 lakh population, P is equal to 100 thousands. So here P is equal to 100, not 1 lakh. So you need to substitute P in thousands. That means when the population is 1 lakh, that means it is 100 thousands. 100 is the value of P here in this formula. So very important, very important. You need to remember the units, otherwise there is no use of remembering these formulas. Okay, these formulas. So this is how we determine the fire demand. Now, so from now, what we have learnt? So we have learnt how to calculate the per capita demand, and also the per capita demand was already provided for us by the Indian Standard Code. So we need to remember those values. We need to remember those values to determine the per capita demand. Okay, to determine the per capita demand or total demand. So once you know the population and the per capita demand, then multiplying the population with per capita demand, you will get the total demand of the community. You will get the total demand of the community. Similarly, what is the total fire demand of that community, that you will calculate once you know the population from these formulas, from any one of the formula. So we can find the fire demand also. In general, this is a formula, National Board of Fire formula, we generally use more for the calculation of fire demand in our designs. Okay, so this is the total part up to which we can determine the total amount of water required. But one thing still left, that is the design life. So before moving into the design life, I would like to discuss one more concept here, that is variation in the demand. So variation in the demand means the demand may not be a constant value as how we are taking. So we are taking that 135 LPCD is the demand of domestic for a LIG group of people. So it is not a constant value. How the demand continuously 135 LPCD they will take? No. They will take one day higher, one day lower. They will take 1 hour higher, 1 hour lower. So there will be hourly variation, there will be daily variation, there will be monthly variation, there will be seasonal variation. So there will be many variations that will be present for the water demand. Okay, so you won't continuously put a bottle in your mouth. So whenever you feel thirsty, you will drink, and after that time you will keep it aside. But whenever you are feeling thirsty, you want that water. It does not mean that so there is no demand of water when you are keeping the bottle aside. We cannot take that hours into account. So you need to take that hours also into account. We will keep an average demand, so that how much you need for a day. That I will give you for that day, so that you can take it any time. So but you need to consume only 135 liters per day, per person. So 135 liters I allocated you. So you use it in the first hour or you use it in the last hour, it does not matter. But you have to restrict your usage to 135 LPCD only for one day. That is what is the concept. Okay. So let us see the variation in demand. So variations in demand. See, for example, demand versus time. Let us take a look how the demand varies with the time. So I am taking a day, one day into consideration. So midnight 12 a.m. midnight. So there will be any consumption during the midnight. Okay, there is some people are consuming it. So let us assume that the demand is, anyways the demand will be very less during the midnight. So when you reach morning 4 a.m. so the demand gradually increases. When you reach 6 a.m. so the demand further increases. 6 to 8 a.m. so the demand further increases. So after 8 up to 10 a.m. the demand gradually decreases. So after 10 o'clock many people go to offices, schools, colleges, whatever it may be. So because of which the demand will go down again at 1 p.m. So again the demand slightly increase because of eating and all. So whatever it may be. So here that means if you look at a number of hours, so the demand is not constant, it is varying. Similarly, this is a simple example of hourly variation. Similarly, if you take a Saturday, so it is a weekend, so you may wash clothes, you may clean your home, so you may do anything, so because of which the water consumption will increase. Sunday you wash clothes, so you clean something, house and all, so you clean your car, so that day the consumption of water increases. Whereas if it is Monday, everybody goes to office and all, so that day the consumption may be decreasing. So that means there will be daily variation, there will be hourly variation. Similarly, if it is a winter season, so the water consumption will be little lesser than in case of summer season. So there will be seasonal variation. So all these variations needs to be taken into account during the design. So the same system, you cannot increase your system during summer. The same system has to feed the water. Okay, the same system has to feed the water in winter. You cannot reduce it or you cannot increase it for when the demand is fluctuating. You cannot increase it when the demand suddenly arises because of any fire broke out. So that means, so the variation of the demand so needs to be considered into account, okay, before doing the design. So there is a variation. So in order to cater the needs to some extent, so you need to increase your design demand. You need to increase your design demand by using some factor of safety. So that factor of safety, actually Goodrich has given a formula for that factor of safety. That is, according to Goodrich formula, as per Goodrich formula, so the peak factor, so there will be peak factor and average, peak demand and average demand. There will be peak demand and average demand. Peak demand by average demand. This is the factor. This is the peak factor. It was given as 180 into t to the power of minus 0.1, where t is time in days. Time in days. So using this formula, we can find the factor of safety. So I told you here the variation will be on a daily basis and the variation will be on hourly basis. So daily, if I want to find the factor of safety for daily basis, so for daily basis, for daily variation, so that is t is equal to 1. T is equal to 1, then this factor, the factor is equal to our peak factor, or maybe peak factor is equal to, so 180, this is in percent, 180% into t is 1, that is 1 only, that means it is 180%, or we can take it as 1.8. The peak factor is 1.8 for peak demand is taken as maximum daily demand and average demand is taken as average daily demand. So here, so this peak factor is for daily basis. That means for daily basis, we take this as maximum daily demand by average daily demand. This factor is how much? 1.8. This factor is 1.8. That means the maximum daily demand is equal to 1.8 times of average daily demand. Okay, the average daily demand. Similarly, what is the peak factor for maximum hourly demand? See here, when we are taking hourly demand, so we cannot leave the fire demand separately. The thing is, when you are taking a daily demand, generally fire demand will only last for few hours. We assume that fire demand will only last for hours. That means fire demand will only present for some number of hours. It will not present for months together, for days together. Whenever there is a fire breakout happens, we will clear that fire breakout in span of hours. So that is why generally if you are taking a daily demand, we don't consider the fire demand into account. But whereas if you are taking a hourly demand, then the fire demand you need to consider inside the hourly demand. Otherwise what happens? You cannot separately add fire demand, because the fire only it will present only for few hours of span of time. Okay, so that is why generally in hourly demand we have to take the hourly demand into account along with the fire demand. But whereas here in daily demand, so on a particular day only the fire will happen. So in that particular day, so only there will be fire demand. So you can add separately. But whereas in hourly demand it is not the case. On a particular day, so not for a particular hour there will be fire demand. It will be some number of hours. Okay. So not a single hour there will be fire demand or single minute there will be fire demand. So there will be fire demand up to 6 hours or 7 hours of time. So we cannot take it separately. That is why generally fire demand is incorporated in hourly demand, but it is not incorporated in daily demand. Are you getting me what I am saying? So here maximum hourly demand is defined like this. Maximum hourly demand is equal to 1.5 times of average hourly of maximum daily. See, listen to this carefully. See, what is maximum daily? If you take a month, 30 days are there. So first day, some value of 10 LPCD is there. Second day, 15. Third day, 30. Fourth day, 50. Sixth day, again 40. Likewise, it is increasing and decreasing, and one day you got the maximum, that is 50 LPCD. On that day, there is also fire demand. On that day, there is also fire demand. So that maximum daily day. Okay. So on that maximum daily day, so one day you got maximum daily. On that maximum daily day, what is the average hourly? On that maximum daily day, what is the average hourly? So on that maximum daily day, what is the average hourly? So the maximum daily demand. So this is the average daily demand. This is average daily demand. So on the maximum daily day, so what will be the daily demand? On a maximum daily day, it is 1.8 Q. On a maximum daily day, so what is the discharge needed? 1.8 Q. Okay, this is the discharge on a maximum daily day. So that is 1.8. So here this value, average hourly of maximum daily day, it will be equal to 1.8 Q. It will be equal to 1.8 Q. Okay, so here, so this 1.8 Q is having an additional factor of safety of 1.5. This is having an additional factor of safety 1.5. I told you, in order to take care of the fire demand, because here fire will exist only for few hours. So that is why you need to be cautious. You need to also incorporate more factor of safety in order to take care the fire demand also. In order to take care of the fire demand also. This is the average hourly of maximum daily is 1.8 Q. Okay, average hourly of maximum daily is 1.8 Q. So, and this is the additional factor of safety. Okay, so in order to take care the fire demand also. So then now it becomes 2.7 Q. 2.7 Q. Where this Q is average daily demand only. Q is average daily demand only. So this Q is average daily demand. So here also this is average daily demand. Okay. So maximum daily demand is equal to maximum daily demand is equal to 1.8 times of Q, that is average daily demand, similarly maximum hourly demand is equal to 2.7 times of Q, where Q is again average daily demand. Okay, so these are the variations in demand. These are the variations in the demand. Now what is meant by coincident draft? and what is meant by the design lives of various components which are coming in water supply system. All those things we are going to learn in the next class. Thank you so much.